Good morning. Many of my friends in the oil industry and the service companies say to me that what they're looking forward to in terms of optimizing production from some of their newer reservoirs is drilling more wells and pumping more fluid in hydraulic fracturing operations. And I tell them, well, no, that's completely wrong, that you want to drill fewer wells and you want to pump less fluid to account for the same production. And frankly, the only way that we're going to be able to do that is to move ahead and more explicitly interrelate the specific geologic environments with the actual engineering treatments that are carried out on hydraulic fractures. And, okay, there we go. As a background, this is where we started, but frankly, we haven't gone too much further than this. The basis of this was analytical work in the Soviet Union and in the United States in the 40s, 50s, and 60s, looking at analytical solutions that were, say based on Snedden's solution, where we completely ignored the influence of geology. Okay? But fundamentally, we really haven't changed even these days, because you'll notice that the relationship that we've got there is just fundamentally lubrication theory for representing the pressure drop between two parallel plates. The industry did evolve, though, ultimately recognizing that geologic controls, particularly in terms of height growth, needed to be incorporated into hydraulic fractures. And the fracturing programs that were developed at that time, particularly during the 1980s, coupled analytical models to develop pseudo three-dimensional representations of hydraulic fracturing height growth. Similarly, at that time, there was an initial drive towards bringing mechanics into the hydraulic fracturing models that were used at that time. Some of the early models then, for example, TerraFrac was one of the earlier models that brought in real continuum mechanics. But once again, we're still talking about continua. As time went on, and particularly with our appreciation for what happens in stimulations and some lower permeability formations that we're dealing with these days, we have to recognize that the discontinuities and a multiplicity of in-situ weaknesses cause complicated hydraulic fractures to occur. And we've had many methods for representing those. And I've listed some of them, and I apologize to those in the audience who I've left off the list. But certainly, we're looking at new and different ways to represent these methods in our numerical simulations. So, in terms of doing this, we have these simulations, but we still are lacking in terms of our ability to realistically represent geologic data in these fracture designs. And in terms of our fracture designs, these are what we're looking to be able to manipulate to come up with a hydraulic fracture and subsequent production that is actually effective. And so these things, as we can see, we have room to vary the fluid type that we're using, the viscosity of the fluid type, whether or not it's a compressible fluid, whether it's a water-based or sometimes even an oil-based fluid, the rate at which we pump, the volume that we pump, and our mantra these days is that we pump more and we pump at higher rates. That's usually economically driven because the fluid of choice, because of cost, is usually slightly viscosified water. We also can maybe do something about the conductivity of those fractures afterwards and possibly be able to control the leak-off in those fractures. So in terms of that, we have these controllable parameters. How can we represent the realistic geologic parameters that we're dealing with? Okay? We need to, number one, take into account the in-situ stresses. But we still are desperately lacking in terms of the industry, in terms of methodologies for determining these, let alone the properties for inferring the natural fracture distribution and their mechanical properties. Although, as you'll hear from the third speaker this morning, we've come a long way in terms of doing that, in terms of being able to represent these, account for them, implement these in terms of numerical models. And then finally, we take these properties, we take these controllable properties and these intuitive in-situ properties or mechanical properties, and we can ultimately relate these to specific geologic controls. And that's one of the goals of work that I'm currently involved with in terms of looking at different geologic environments, trying to infer characteristic signatures for hydraulic fractures, both during large volume treatments and during small treatments that are designed to infer properties of the reservoirs. We commonly call those diagnostic fracture injection tests. So in terms of these, let's look at them. We're certainly interested in the tectonic setting. Coincident with the tectonic setting is the contrast in stresses. Certainly vertical variation in stresses. And this is a three-dimensional problem. Most people in the petroleum industry, in terms of, certainly in the hydraulic fracturing side, considered the minimum principal stress as being the dominant stress until really rather recently, when it was acknowledged that, well, shearing really could have a role in terms of stimulation that was being carried out. Certainly then, on top of this, in these geologic settings, superimposed upon those geologic settings is the fabric of the rock, the discontinuities, the bedding, the ability to have mechanisms that will arrest fracture growth and cause losses of energy. And certainly this is always coupled with formation pressure. One of the things that we always look for as production engineers or completion engineers is we're looking for high pressure environments, because that dramatically improves the drive into the from the reservoir into the wellbore. Finally, what we have, and this receives a lot of press in the petroleum industry, is what I call energy release. Energy release is conventionally known in that industry as brittleness, and it's usually misrepresented. What we're looking for is formations where there can be a preponderance of effective fractures, and some sort of engineering activity can create a substantial number of additional fractures. So in terms of this, we have these geologic features, and we also have these numerical capabilities. So what's a workflow in terms of representing these in our numerical model? So the first and foremost has to be some sort of measured, intuitive, statistical, intelligent assessment of the fractures, discontinuities that are three-dimensionally present, their frequency, and then on top of that, our best inferences of what the mechanical properties are along those particular features. Once we have represented that in a numerical model, as I mentioned, there are currently a number of models that have been developed commercially at national labs, academically, that can do a pretty good job of representing growth of hydraulic fractures in a multiplicity of weaknesses that are present. And then finally, and the one thing that really has not yet received all that much attention, is taking those predictions of hydraulic fracturing growth and superposing those directly into some sort of reservoir simulator that is going to represent production from those particular situations. Now, the one program suite that I'll talk about that I'm familiar about is what we've basically used as Itasca. And one of the reasons for this is that it was commercially available, and there were codes that provided a reasonable start for representing multiple fractures in a fully coupled mechanical, thermal, hydraulic, and presumably also chemical media. This sort of discrete element method can be at least soft coupled and sometimes harder coupled to reservoir simulators, and indeed that's what we're doing with an in-house reservoir simulator. So taking the forecasts of hydraulic fracturing that were created with a distinct element code, taking those forecasts of fracture extent and aperture, and taking those predictions and importing it directly into a reservoir simulator, which similarly could represent those exact same features and which would have coupled geomechanical behavior to allow change in aperture, extent, and production that is accordingly related. So in terms of this, unfortunately, off-the-shelf codes are sometimes difficult, although they are involving. In its original format, these codes basically mandated that all features had to be prescribed, all discontinuities had to be prescribed, and have finite apertures initially. So that means that as soon as an aperture is in contact with pressure, you are going to have that aperture opening up and sensing fluid. So one of the first things that, needless to say, one has to do with a model such as this is you have to put in some sort of a propagation criterion. And the one that we basically did was really quite simple, that we just stitched the fracture shut. Once the pressure reached, stitched them every fracture shut, prescribed them in advance, stitched them shut, and once the pressure reached a prescribed level that met some sort of a fracture mechanics criterion, mode 1, mode 2, no mode 3 in this case, but at least those two modes, then that stitch would be broken and a finite propagation could occur. Similarly, in most cases, these codes were representing impermeable matrices. Now, that at first, 5, 6 years ago, I thought that was reasonable. But actually looking at production and injection into many of these tight shaly formations, you can really see that this is problematic and that having impermeable matrix blocks just does not make sense. Let's look at it this way. In a typical hydraulic fracturing operation, an operator may pump 5, 6, 7, 8, 10,000 gallons of fluid. And he's ultimately going to produce some of that fluid back to kick off gas or oil production. The amount of fluid that he produces back is maybe 30% of the injected volume. So you have to say, this fluid went somewhere. It either went to fractures that are no longer communicating with the wellbore, or to situations where a substantial amount of imbibition has occurred in very small pores. And so really, it is quite relevant, and we just basically changed this by adding sinks to accommodate fluid loss. We still have not sorted out proppant, and so that's why I'm waiting to hear what Joe Morris has done in his talk this morning. He's going to be able to give us the answers to that particular issue. Wasn't that cowardly? Anyways, so here we are. Okay, we have possibilities to represent the geologic environment. We have possibilities for doing the numerical methods, but we do have challenges, okay, that we can deal with. The challenges include the computational expense of these programs. That's improving. And certainly, the consequences remain in determining the adequacy of the in-situ properties and importing those properties into the models. And that's why one of the programs that we are embarked on presently is trying to do a large number of simulations in different extreme geologic environments, ranging from, say, passive margins through foreland basin, through shear and thrusting, strike slip and thrusting regimes, where in each particular case we're looking for characteristic signatures that can exist when you're hydraulic fracturing, and also looking for the consequences in terms of production. And so the purpose of this is basically you can develop an exploration tool that will complement conventional exploration tools. A conventional exploration tool is going to say, I have a resource present. If I have signatures of how hydraulic fracturing can potentially behave in different tectonic and basinal settings, I have a possibility for having another tool that's going to say, well, even if I have a resource, I cannot convert this resource to a reserve because the completion and stimulation is just going to be too difficult. And so you can look at these, and you can look at these situations in level of increasing complexity, moving from a passive margin through a foreland basin, through a thrusting regime, and you can kind of imagine that there are going to be different hydraulic fracturing regimes that we are in fact trying to duplicate. So imagine that if you're in a passive margin situation, that's a situation where by virtue of the substantial contrast in the stresses, one of the likely, but not necessarily the only likely consequences, is a monodirectional fracture. So from the perspective of a completions or an engineer or a petroleum engineer, what you say to yourself is, look, I want to take advantage of that single dominant fracture being present. I'm going to pump a very viscous fluid into that fracture, and I'm going to develop a fracture that has very high conductivity. That's opposed to a situation such as in a foreland basin, where by virtue of repeated uplift and burial history and the complexities of the tectonics that have gone on, you can have a multiplicity of pre-existing fractures that are present, and consequently you can develop a hydraulic fracture that's much more complex, and you're going to have to select a hydraulic fracturing methodology that probably uses a less viscous fluid and can penetrate into all of these fractures at once. It even becomes more complicated when you're dealing with a shearing or a thrusting regime. Just the complexity of the stresses, the magnitudes of the treating pressure, hydraulic fracturing pressures that you're talking about, and the complexity of the fractures. So it all boils down to ultimately we're developing an atlas that comes up with signatures that look like this, with precautions for how those fractures might grow and the morphology ranging from something that's relatively simple in a passive margin situation to something that's very complicated. The Tarim Basin in western China is a very, very good example of the fracture shown at the extreme right. So in terms of that, that's one layer of control on the growth of hydraulic fractures that can have geologic features that are superimposed upon it. The second level relates to the nature of the in-situ fractures that are present and what those fractures are doing. Now, these two situations that are shown here show fractures that are developed on a regional scale, as might exist in the Antrim Shale, and fractures that are associated with folding. Those two fracture systems are going to create dramatically different hydraulic fracturing behavior. One will be associated, at the left, will be associated with a relatively diffuse, aerially diffuse, large-scale fracturing situation, whereas the one at the top could be a situation where vertical growth of the fracture can be dramatically impeded. And studying vertical growth and how energy is lost as a fracture moves towards bedding planes certainly is one of the areas where so many people in the industry are studying hydraulic fracturing these days. So just to finish it off, maybe just a few examples just showing how this is important. The scenario at the left, basically very simple. These are two intersecting fractures. Well bore is shown. And if you do not represent fluid loss, you're definitely going to overestimate the complexity of your hydraulic fracturing situation and the magnitude of the ultimate production that you'll be getting from these situations. Treatment rate, basically what you can see is that treatment rate, depending on the in-situ stress field, may or may not have a substantial influence, but it is something that can be impacted by specific geologic characteristics. Where one really sees a difference is in terms of, say, viscosity of the fluids. Okay? Typically, if the fluid is even a slightly higher viscosity, I mean, going from straight water on the left to viscosified water on the right, you see a dramatically different pressure signature, and that's all we can work with as engineers, those pressure signatures, as in terms of telling us what's going on, because that's what we see at the surface. A dramatically different pressure signature and a dramatically different geometry. The more viscous fluid is more monodirectional, less secondary wings, and production is going to be substantially different in that case. So this goes on, and basically you can go ahead and you can do a number of these simulations. In this particular case, I'm not sure that the movie is functional because it's being shown on a Mac, but that's quite all right. It doesn't matter. I'm running out of time anyways. Okay, we don't have time for the movies. Okay, but the principle is that this is a situation where you can see, depending on the angle of offset between some sort of propagating hydraulic fracture and the bedding plane or interface or whatever, that fractures can be arrested, fractures can be transmitted through, fractures can follow the bedding plane. And this is one of the big challenges for simulation in the industry today, trying to understand the degree with which bedding planes serve as energy sinks and impede the vertical propagation of fractures, or are basically ignored and fractures grow out of zone. Now, there are two cases where this is relevant. Say the Bakken formation that we often hear about. In the Bakken, if fractures grow out of zone, then basically you can be pumping hundreds of thousands of gallons of fluid that are fundamentally not going to do any good for your production. Alternatively, in the Vaca Muerta in South America, you have a situation where you have a fabulous reservoir. Extends over maybe 1,000 feet. But fractures may not grow that full 1,000 feet because of the energy dissipation once hydraulic fractures hit these particular boundaries. And I think we'll hear more about this in another talk today. So the final piece of the story is you have to take this information and actually include it in reservoir simulations. And this is just an example. The specifics are not important. The relevance is that the coupled characteristics that we talk about so often in terms of fracture mechanics have to be carried over into simulations that talk about how production occurs from natural fractures in terms of fractures having finite compressibility, and that compressibility altering the production from individual arms, closing off certain ligaments of fractures so that this fracture pack, these fractures out here may ultimately be completely isolated from a wellbore that's down here, strictly because of closure of communicating fractures. So the bottom line is that we have a very, very exciting field that we're dealing with now. We have the methodologies to come up with initial determinations of what the fracture geometries are. We may have to decide in terms of sacrifices that we have to make in terms of representing these fractures for numerical feasibility. Computational efficiency is improving. I think the greatest challenge that we have in our discipline, to a certain extent, is defining the in-situ property specifically. And that can be done in a couple of ways. In terms of large-scale tests, actually, so there's some talks going on in the room right next door right now about how to determine properties of in-situ discontinuities. And secondly, using numerical modeling like this as for back analysis and for inferring signatures of particular joints, geologic systems, or whatever. So I think there's great challenge, and really our ultimate goal here, as I said at the start, is that we want to go to a situation where I don't want to drill more wells, and I don't want to pump more fluid. I want to drill fewer wells, I want to pump less fluid, and I want to produce equivalent amount of resource. And at this point, I'd be happy to try and answer a couple. Do I have a couple of questions? If anybody has questions, critiques, observations, threats from North Korea.
Let's give our speaker a hand. Any questions? Yes.
You mentioned the role of viscosity in controlling what happens at these intersections and so on. Some authors have discovered under certain limits that the product of pumping rate with viscosity is the dominant one. But I can imagine there are circumstances where it's not just the product, but maybe some subtleties on top of that.
Yeah.
Do you think that captures the first order effect?
Yeah, absolutely. And for quite some time, I've been looking for a dimensionless parameter that could combine those two things. So the question was that, you know, there's evidence that viscosity in a complicated fracturing medium can lead to a more simple monodirectional or pseudo-monodirectional, or at least confined path for hydraulic fracturing growth. And Dr. Morris has also pointed out that in addition to that, rate can also be an effect. The situation I showed in that one particular case did not show being rate particularly important. And that was in a situation, I think, where probably the stresses were arguing strongly against rate. But there also is substantial field evidence from microseismic evidence and actually I think from some tilt meter evidence that suggests that high rate can also accomplish the same thing as viscosity. And it kind of makes sense. If you look at it, both of those are methods that are causing viscous losses in relatively narrow features. And if you have a secondary fracture with a smaller aperture, that smaller aperture is going to cause additional viscous losses, either caused by rate and or pressure, and it's going to inhibit the fracture from growing into those secondary features. And so this is one of the tools that can allow us to control the morphology of hydraulic fractures.
Okay,
Thanks.
You.